All right, so we're going to go ahead and get started. So as you know, the first main mapping projects are due today, and we've already received a few of them, which is good. And so for everyone else, please do be sure to send them by midnight tonight. And then we're going to start grading them quite soon and hope to get you that feedback both on the mapping and on your report so that you can incorporate that information going forward. Are there any quick questions about that first assignment? Nope. Looks like, is there a UNR question?
That was just one question. We just, do we need to submit the hillshades or just the GIRs and the mapping in the zip file?
Correct, yes. So all the shape, all the line work and GIR files, and then your written report, but we definitely don't need or want any of the data that you've processed. It'll be much easier to not send it. Are there any other questions?
Not from class.
Okay, so we're going to start the second project today. And just an outline of the next few days. Today we're going to discuss, similar to the last class, we'll outline the projects and then we'll go over how to access the different data sets, particularly those that I didn't send you. Even if you don't need these data for the second project, please do pay attention. These are just quite useful GIS skills that we've received several questions on throughout the weeks. And so I think everyone will benefit from hearing this material again. And then as soon as you get that first project turned in, we would like you to start working on the second project. Hopefully spend an hour or so at least before next class, starting at least access the data and think about what you've been asked to do. So then next Tuesday essentially be an office day. So you do have to come in, check in, and then we'll discuss any questions. And it'll be a time then for you to start working on the mapping. And all the instructors will be here online or at UNR for you to ask questions too. Then later in the rest of semester, we are going to have more of those breakout sessions. And so every Thursday going forward is going to be a breakout session. So again, please come ready to discuss, troubleshoot with your classmates and make the best of that opportunity. Are there any new questions? Okay, so I wanted to spend the rest of today going over the assignments as well as some just general GIS procedures that you'll be applying in the course. So Rachel and I have both received a question from a few people during this semester, which I wanted to review in class with everyone here. The question is essentially, so my DEM is in units of degrees. How do I convert the resolution in units of degrees to meters. So I'm going to show you how to do that today. I'll emphasize that this unit or degree to meter conversion, it's very important that this is something that you internalize how to do and really can do going forward without too much thought or stress. So here is the Idaho data set, which many of you looked at for the repeatability part of the project. And in the repeatability for all of the mapping, we asked you to tell us the resolution. And so if you want to say that the resolution in meters, you want to go through this procedure to figure out what that is. So it's always good when you get a new data set to look at the metadata, essentially data about the data that you have. And so this is what the metadata for this Idaho data set looks like. So it tells you the CRS is the coordinate reference system. Something's always good to look at. This is the EPSG code. So each coordinate system has its own 4 or 5-digit code. And this latitude longitude is one of the most common ones. So you'll see this as well as other longitude and latitude coordinate systems quite frequently. So then the extent here tells you in degrees the corners of your data set. So if you look here, you should already see, those numbers, those are what many parts, at least in the northwestern US, it's about what I would expect for the degree. So I bet this data set is in units of degrees. And then the next thing to pay attention to is unit. So then here we see it says degrees. So again, that confirms what we thought by looking at the extent. And then you can come down here to the bottom of this page where it says pixel size. So this is the size of each pixel in the raster or grid data set. And you'll see that they're different. So this is often the case for data in longitude and latitude. And the x coordinate or the longitude has a unit or distance of 2.16 times 10 to the negative 5 degrees. And then the latitude or y is negative, often has a negative, it's just a different direction. But it's essentially 1.55 times 10 to the negative 5 degrees. So are there any questions about how to find this information or how to interpret it? So in summary, we really want to pay attention to are the units, turn degrees here, and then the pixel size. So then if you want to convert pixel size to degrees of, or units of meters, which is often what you want to do because it's easier to understand, then have to do some math, which is PowerPoint. So how to convert degrees to meters. So in this case, took the number 2.2 times 10 to the negative 5 degrees of longitude. We want to convert that to meters. So you've hopefully seen this formula here. It's really important that you remember this, memorize it. That 1 degree of longitude is equal to about 111 kilometers times the cosine of the latitude. So we know that Bora Peak is about 45 degrees north. You can look that up just on Google. So then we can apply this formula to figure out what 1 degree is. of latitude at 45 degrees north. Start with 1 degree. That's 111 kilometers times cosine of the latitude, which is 45. So cosine of 45 is 1 over the square root of 2. And this then is equal to 78 kilometers or 78,000 meters. So then we can go back to our distance in degrees, which is 2.2 times 10 to the negative 5 degrees. Then we're going to multiply that by 78,000 meters divided by 1 degree. And that tells us that in the longitude, our pixel size is about 1.7 meters.
Are we expected to convert all of this within QGIS, or is this just for the report? Or
so in the report, you are asked to state the resolution of your data sets. And so if your data set in QGIS is in units of degrees, then this is one approach to converting those degrees to meters.
okay, so you want the resolution in meters.
Ideally, because it's easier to internalize. If you put it in degrees, it's okay too. But Rachel and I have gotten a few questions throughout the semester about how to do this process. And so that was my motivation for speaking about it today.
Okay, thanks.
And again, it's this formula here is very important that you just know intuitively how to apply this formula, essentially to go from degrees to meters or kilometers. And so, yeah, this is quite important to be able to do. So that's why we are going over it right now. Any other questions? All right, so for the next report, if you're still finishing up this first one, please try out this formula if you're doing any conversions between degrees and meters. Okay, so now we're going to discuss the second set of main mapping assignments. First, so I believe I sent everyone their second assignment yesterday. Is there anyone who didn't get an assignment?
I haven't gotten mine.
Who said
This
that?
is Rachel. This is Rachel Mikender.
Okay, I'll check and send it to you right after class today.
Thank you.
So I'll go through each of the assignments now, essentially what you're doing and what some of the motivation is from our perspective. So almost everyone who did not do the repeatability the first time is going to do it the second time. And the idea here is that everyone completes 5 maps that each is about 2 kilometers along strike of an area that later ruptured. And so all these maps are meant to be difficult in some way. We're essentially looking at how you as mappers are able to map correctly in these areas and how your maps also differ from the later ruptures as well as from each other. And you must do the morphometric and or geomorphic map for one area and turn this in with a professional looking map. However, we do recommend that you do this initial mapping for all 5 areas. And for speed, if you prefer, for example, you can just print and then do this mapping by hand. You don't need to make that professional scale looking map at the end. And then several other people are going to be completing new pre-rupture maps for the Nura and Denali earthquakes. So for Nura, you want to get pre-rupture imagery from Google Earth, and I'll show you how to save that in a few minutes. And you can also use SRTM topography you can access from Open Topography. And then a few other people will be looking at Denali. And so there's 2 areas of the rupture that I would like you to map based on the digital elevation model, as well as the ortho map that I sent to you. And I'd like to emphasize that this data is a private data set from the USGS that was shared in confidence to Rich. So like some of the other data sets in this project, please do not share that data outside of this project. A few people are going to be looking at data quality, for example, along a fault in southern New Zealand, along the southern San Andreas, and the Wasatch Fault. So what we're trying to understand with these maps is how, or what's the utility of a higher resolution and higher quality maps relative to other data sets. And so I sent you a list of the data sets that you are going to be using for the mapping. The idea is that you start with the top data set, so that's SRTM topography, and you build your map in the area in the polygon just from the SRTM topography. And then you send us that the map, GIR and the fault map that you make from the SRTM topography. And when that's done, can then move on to the second data set, which is, I believe, air photos and or aerial imagery, satellite imagery on Google Earth. And so, yeah, you're using data sets with increasingly higher information. And once you move on to another data set, you definitely cannot go back and edit the earlier maps that you made, even if you have new insight from them, for example, on something that was in the earlier data set that you just didn't notice. Are there any questions so far?
I have a question. For the data quality, do you completely start over for the second set? Or do you take what you know from the first set?
You can take your files from the earlier one, but be sure to fully update them. So faults look like they're in a different position, faults are geomorphic features, or they've disappeared, or you see new features, then make sure that you fully update your map to be consistent with the new observations.
Okay, thanks.
You can also restart if you'd like. It's up to you.
Basically, the fault mapping should be an independent for each data set.
Yes. Well, I'm letting you start with what you had before, as I'm assuming that it's still kind of in your mind. And so, but yeah, if you want to completely restart and be independent, at least on the mapping, then that's fine. And then Two projects are going to be looking at the impact of a geologic map. So this is for El Mayor-Cupica earthquake in northern Mexico and Napa in California. And so the idea is that in that polygon that I sent you, you're going to first map from topography and imagery, like in the other exercises. And about halfway through the project, you're done with this initial map. You'll send that to us, and then we'll send a geologic map for both of those areas. And for EMC, a couple of papers, so that you then gain some degree of local expertise. We want to understand how that additional information impacts your mapping. So again, for these areas with the geologic map, again, you can add, subtract, revise your earlier point and line work. And you are allowed to start from what you had before, but you cannot edit the map that you made before you received the local expertise. Are there any questions? Comments?
Yeah, we'll have time for questions on Tuesday. Got a chance to look at the database.
Yes.
Given, stuff like that.
So I wanted to do some brief demos of things you've shown before. Again, maybe you didn't do some of these activities for the first, and so I think this demo will be helpful to you. And Rachel and I also received questions on how to do these demos during the past doing these activities. So again, even if you're not sure they're going to be useful, I suggest that you pay attention. So the first thing that we're going to do is I'm going to show you how to save high resolution imagery from Google Earth. So for example, you may be interested in doing this if you're doing the Nura earthquake or some of the pre-rupture mapping for EMC or Napa. So I want to open Google Earth. So Google Earth has an enormous amount of imagery, but you can't export it in a way that's georeferenced. And so today I'm going to show you how you can export imagery. And then once you export it, highest quality imagery that you can get, you'll then send it to Rachel, who will georeference it for you and then send it back to you. So I'm going to go somewhere here in Arizona. And just a little trick. So when you save this imagery, you always want to be looking straight down, satellite terminology, being the nadir angle. And you want north to be aligned the vertical axis, the image. And so to do that, you can press R, which I already did, which then puts us in this nice reference frame. Down here, you can see the imagery date. So this is from 2019. And you can go to this clock up here and see older imagery. So if you're doing a pre-rupture mapping, you want to make sure that by the time you zoom in to where you can see anything, that you're looking at older imagery before the earthquake in the area where you're mapping. So Google Earth will let us save and export imagery. So to save, you can go to File, Save, and then you see it says Save Imagery. So then you have these different resolution options. We want the best imagery for your mapping, so you always want to save at the maximum. You can see that lets you save an image that will have about 5,000 pixels in the east-west direction and 3,000 in the north-south direction. And so we'll want to zoom in so that we have about 5 kilometers in the east-west direction, which will then let us save imagery at the highest quality because these images have about a 1 meter resolution. So here's the ruler. I always want it to be in kilometers. So we'll see what this length is. So it's 3 kilometers. So we can zoom out. And then measure again. So now we're at about 6. So let's just zoom in a little bit. So now it's about 5 kilometers. And then you see here, it did reset the resolution. So then we want to come down here to put it at the maximum and then go File, Save Image. And then, so I believe, and then you want to click here and then it'll let you save it where you want on your computer. So if you're looking at an area, say you save this image, then if you want to save another image, it's best actually if you don't change your zoom at all, because then you know that you still have that 5 kilometer length along the east-west direction. And then you'll just want to move it so that you have a little, but not too much overlap with the next area. So here I just moved the screen, and now we have some overlap here to the south with the northern part of the image we had before. So we can then just go save image and then go so forth and save imagery in the whole rupture area where we are going to do the mapping. Are there any questions?
I'd say a tip too for this, when you're toggling between the ages for the rupture, you could see kind of on the screen that it might have been from 2 different ages where they took it, because there's some kind of like major discoloration between them. So I would, for the area, try to toggle to a time where the imagery is still clear, but it's also not, there's not like a stark difference, because then you'll know that it was taken at 2 different times and it won't be as like consistent across the whole landscape.
Yes, it's a good advice. So here it's not too problematic, but in other areas, I think generally higher latitude, you do get some stark contrast. Max?
Yeah, my question is, I'm working on Denali, and you said we exclusively have to work with richest data, so I don't have to do this, right?
Correct.
Yeah, okay.
For what
Because
is
if I'm looking at it, it's gonna spoil me, right?
yes.
Okay,
And for what it's worth, the Google Earth imagery in Denali is covered with snow.
Yeah,
The older
all right.
imagery, so it's not going to be super helpful to you.
Great, okay, thank you.
Are there other questions? Nope. Okay, so we'll review how to get high resolution topography from Open Topography. So you'll want to go to opentopography.org, where you can Google search Open Topography. And next thing you want to do is go to data. So I'll show you the process for the Napa region. You'll want to apply a similar process to any of the data sets where you're doing the mapping. Napa is just to the north, the Bay Area. You can see Napa here. I did happen to know where it was, but hopefully the polygon that I sent will help you orient yourself for where you should be zooming into for open topography. So I'll draw a polygon in this Napa region, and you'll see that there's two data sets that cover Napa. The first is this August 24th, 2014. And so this data set was after the Napa earthquake that you're doing the mapping for. So you definitely don't want to get this data. And you can come here, you'll see that the survey date was September 2014 and the earthquake was in August. So again, this is a good check that this is the post-earthquake data, and again, not with the data set that you want. And you'll zoom down and you'll see that there's a second data set, Napa watershed. Click it, you'll see that it was collected here where it says survey date in 2003. So this was definitely before the 2014 earthquake. So then you want to access the point cloud data. So you'll come here where it says point cloud. This is then some basic metadata about the data. You can zoom in here, zoom out just for get the scale. So where this red polygon is, that's where, or the spatial extent of this data set spans the pre-rupture data for the Napa earthquake. So then also I would like you to pay attention to is where it says choose return classification. So you have the option of ground and or unclassified. Selecting both of these is the default, as will essentially generate a digital surface model. So this includes the ground surface, which is the bare earth, but then also buildings and vegetation. And for some areas, you definitely want to look at this product and see what it looks like. And so you can leave both of those checked. And then open topography will output a digital elevation model. The default for most data sets is to grid at 1 meter. So that's your resolution, and that's fine. So you can then just come down, leave all these settings as they are. And so you want a job title, good to be descriptive. So fault mapping, Napa, digital surface model 1. So then can press submit. And then so this job is being processed by open topography. And then in a few minutes, you can come back and we'll have a digital surface model at the area of interest. And then for fault mapping, it's often advantageous to also generate a digital terrain model. So this is a map of the elevation where you removed everything but the bare ground, bare earth. And so you've thrown out the vegetation and the buildings. And in places of higher vegetation, such as Napa, building a digital terrain model is often very important for being able to visualize the faults. You can leave all the other settings as they were. If you don't move this box, then you'll know that you'll have the exact same area for both the digital surface model and the digital terrain model. So then the only change that we want to make is instead of having ground and unclassified points, the idea is to have just the ground points. So initially we had 90 million point cloud points that were being processed. And then when we turn off the unclassified, we just have 28 million. So we've really decreased the number of points because we removed all the vegetation and buildings. And so this emphasizes that there really is a lot of vegetation in the Napa area. We're probably going to be able to see a lot more detail on the faults by removing the vegetation. You can then leave all these other options the same. And then just to help for bookkeeping, previously we had a digital surface model, but because we removed the vegetation, we're making a digital terrain model. Let's change that S to a T. We'll then let that process. So this first example that we're started running is still going, but I'll look at it in a few minutes and see what the finished products look like. So the other thing that almost everyone will want for this project is the shuttle radar topography mission data. So to do that, again, you go to data, and say we're looking at we'll go back to the Napa area again. So SRTM topography covers almost all of the mapping areas. Although you can't see it on this map, it's still there, again, for most of the Earth. So say we're interested in generating SRTM data for Napa, put a big box there, and then you can zoom down. Again, you see where it says high resolution topography. So this is what we saw before. An SRTM, it's not high resolution, but in fact, it's a global digital elevation model. So you'll want to come here. There's lots of these global elevation models. Many of them were collected after the earthquakes that you're looking at, and so they're not pre-rupture imagery. But here we have the shuttle radar topography mission, which I believe was collected in 2001. And so it's pre-rupture data for pretty much most of the areas where you guys are working on. So that's why we can use it. And then you'll come here and you'll see there's these different versions of the data. So the one that you want to use is the SRTM GL1. So this is 30-meter data. This is all GL1. Ellipsoidal is also 30-meter data, but in a different coordinate system. And then the GL3 is the 90-meter data to reference, is what I used for a bunch of my PhD work. And then since then, the 30-meter data has been released, which is very exciting. So we'll click that. Again, here we get the metadata for this area, survey date. So in fact, it was actually collected in 2000, not 2001. But again, it's still pre-rupture for most of the areas in this project. And because this is 30-meter data, you can process actually quite large areas if you're interested. So yeah, here's the Napa area. And then for the shuttle radar topography mission data, essentially just want to leave the default settings. And then you probably want, again, a good title. So SRTM Napa. In case you want to process many, we'll call this one 1. And then you can press submit. Are there any questions? So you can come back and look at the processed jobs. So here is the DEM. So in this case, it's a digital surface model. And you can download this tar.gz file. You can open it. I think it's easier to open most of the time on a Mac. It's downloading. You can just Mac click it a few times and it'll open into a TIFF file. If you have a Windows machine, I believe if you use 7Z twice, you can get to the TIFF file. And then download the digital terrain model. You would apply a similar procedure to this second job that we processed. And then a similar process to download the SRTM data. Are there any questions? Okay, so one more topic. So Rachel and I have also received a couple of questions about how to make a hillshade or a slope map or contours from data that's originally in latitude and longitude. So for example, this is the Bora Peak data or any SRTM data that you download. So you can follow this link here, which I'll put in the chat. And so if we go to this page, then this will tell us about how to produce these topography derivatives or data that are originally in latitude and longitude. And the challenge with these data is that the horizontal and vertical coordinates are different. And so we have to tell the GIS software what the vertical exaggeration is. So if you use any Esri product such as ARC, you'll have the option of setting the Z factor. So you'll want to come down here and it'll tell you the Z factor that you need to add to compute any of these products, and you want to choose at least approximately the Z factor according to the latitude of the data set. So Bora Peak, we're actually at 44, not quite 45. And so this value at 40 degrees latitude is sufficient. If the data set had elevation in feet, which a lot of American data sets do, you would want to be sure to grab this value instead. So you'll take the Z factor, in this case in meters. And then go to QGIS. So again, here's the DM for the pre-Bora Peak area. You go to raster analysis hillshade. So you see these options. So we just copied the Z factor. So I can simply just paste it there, and then this will generate a correct hillshade. QGIS gives you the option instead of stating the scale. So you want to state one or the other, not both. And the scale is the reciprocal of the Z factor. So let this run. Takes a couple seconds. Are there any questions so far? All right, so when this pops up, it's actually all I wanted to talk about today. So I'm happy to stay online if there's any more questions. Otherwise, we can finish early.
I think another good thing to do is that something that came up in our breakout room is how to like extract by mask in QGIS for the DEMs. Like I'm working on Bora Peak right now, and the DEM is like way bigger than what we need. So yeah, like doing an extract by mask to the shapefile mapping polygon, maybe doing a tutorial of that. I figured it out on my own, but if you want to do that, that would be great.
Would you like to show us?
Yeah, 1 second.
Not sure why.
I'm running a hill shade, so hang on.
This should be much better.
Remove layer. Screen 1. Can y'all see that?
Here.
Good?
Yes.
Okay.
See it.
Okay, let me think here. Sorry, I already did it. So let me. I'm not ready, sorry. Okay,
Okay.
yeah.
Put you on the spot quickly, so thank you.
Okay, so we're given this data. Hang on, let me get rid of this. Remove. Okay, so you're given this, and it's way the heck bigger than what you need. So what I did is that I took Ramon's advice and I looked up how to clip this in QGIS. And so what you do is that you're given, you load your mapping polygon into QGIS, and then you can click on your DEM that you're given, and you go to raster extraction, clip raster by extent, and then you can check that this is highlighted. You go to clipping extent, calculate from layer, Bora Peak clip extent, and then I saved this. I already did this, so I'm not going to do it again. But basically, like you saved a file, you go to your thing, you do the thing, and then you can load in your hang on. You can load in your clips DEM, and then you can see that there's 2 DEMs here. So if I zoom in, you can see that there's a different DEM that's clipped to the mask of the polygon, and now you don't have to deal with all that extra DEM. And then you can go through and do your hill shade analysis on these, on this data, which will take much shorter amount of time in my experience. So yeah, that's how you do that, I guess.
Great. Thank you for sharing. Are there any questions for Mara on how to do that?
Also, it's a quick Google search, so like, don't worry about it.
Like
Extract by mask.
Yeah.
Yeah.
QGIS.
You can make like a dummy polygon layer too if you want the extent of the DM to still be a little bit bigger than the mapping polygon.
Yeah.
You can make just like a random polygon to and extract to that instead of the mapping outline that we gave you to.
Sorry, I was trying to copy and paste and missed it.
All right. Any questions, comments? Anything you want to add, Rich?
No, I think that's great. Just on that last topic, if you go a little bit wider, you can see how the faults might be coming in if you want to inspect a little bit broader from the polygon. But yeah, that's like a great technique to reduce your processing time. So thanks, Mara.
Actually, yeah, that is a good point. You do get
No problem.
better context at a bigger spatial scale for Bora Peak. So
Yeah, I'm gonna do that.
yeah, but I agree, especially if, like, for the contours, that clipped areas definitely much better. All right, well, I'm happy to end class. You can take,
I just have one more comment, Ms. Rich. You were talking about the classified versus the unclassified points with the LiDAR point cloud download. I just wanted to say that in some places where you have the trees, like where there's so many trees, like on the San Andreas Fault or whatever, you don't get a whole lot of information by looking at the classified points, right? But in other places like Napa, there's some places where there's oak trees and little shrub forests and stuff, and sometimes vegetation will grow, will not grow in sag ponds or places where it's wet, or or sometimes they align along ridges and stuff. So looking at the that data set just provides another view. Sometimes the vegetation can actually give you some insight on the location of the fault. Sometimes not. So it's good to look at both LiDAR point cloud data sets, which is great, and that just gets back to looking at multiple data sets as well, like air photos versus SRTM and whatnot. But the two different LiDAR data sets sometimes can give you different insights.
other thing also is data sets are not always well classified. And so sometimes the ground actually just takes out too much. And you're left actually with very few even of the ground points in areas, particularly if there's a lot of vegetation. And so it's another reason for doing what Rich said, which is, yeah, look at as many products as you can to be able to visualize the landscape.
Did you mention the reading too, Chelsea, coming up? Alpharetta?
Yes, so we'll be reading, so we'll talk about that next class. You put it on the calendar, Rachel?
I'm gonna update it right after class.
It's downloadable on the website already.
Oh,
So in April, we're going to be reading 2 papers, both highly related to this class. So one is looking at an analecta of the ruptures from the Napa earthquake, and the other is basically a summary of a somewhat similar project looking at the repeatability, some of the uncertainties in extracting geologic maps from, or extracting geologic data from topography. And so we'll be reading and discussing in class 2 papers during the month of April. So you will have a little bit of homework beyond just this, beyond the mapping assignments. And so we'll put that on the website, and then I'll discuss it in more detail on Monday. All right, well, we're finishing 20 minutes early, so use this time either to put the final touches on that first project or to start looking at some of the details for the second project. And Rachel, I'll send you the mapping, your mapping assignment right now.
Thank you.
thank you.